Hi, statisticians. Welcome to the section 7.5 lesson. So last time in section 7.4, we went from having a random variable x to considering all these little groups inside of basically this random variable, inside of this set of data. We considered a bunch of little subgroups of the same size, and we found the sample mean of those groups, and then looked at this distribution, the distribution of the means. And when we did that, we saw in the one example that we did, we saw that the distribution had a generally normal shape. And I kind of hinted maybe this is not a coincidence, and so we're going to formalize this today. Section 7.5 is about a very important statistical fact called the central limit theorem. Now, theorem just means fact. So this is a fact about central limits. All right, so let's start with a warm-up. Number one says compute the z-score for x equals 8, given that mu equals 10.2 and sigma, the standard deviation, equals 1.4. So we'll use our trusty formula, which you may or may not have memorized at this point, but if not now, then you should soon. So z equals x minus mu all over sigma. So I'll plug those in. Everywhere I see an x, I'm going to put an 8. Everywhere I see a mu, I'll put a 10.2. And everywhere I see sigma, I'm putting 1.4. Now when I throw that into my calculator, I find a z-score of negative 1.57. Number two is pretty much the exact same problem. Compute the z-score for x equals 12, given the same mean and the same standard deviation. So again, x minus mu all over sigma, just a different x value. So now I'm plugging in x equals 12. Mu is still 10.2, and sigma is still 1.4. And when I throw those into my calculator, I get a z-score of 1.29. Now, number three, this is kind of seems like the common procedure at this point. Number three says find the area between these two z values on the standard normal curve. So we'll use the table in the section 7.3 notes. Hopefully you have that marked in your note packet. I don't actually have it in this document, so I'll just write down the values that we get though. For z equals, let's see, I'm going to do the larger value first. So for z equals 1.29, I find the area 0.9015. And now, if you haven't done this, pause the video and then get these two areas. Verify that you can get both of these. Hopefully you've gotten both of them on your own. The second one, the area for a z-score of negative 1.57 is 0.0582. And so the area between these values is just the larger one minus the smaller one, so I am getting 0.8433. Now notice I didn't say anything on these about how we round these values. And I won't say anything about how we round these. Your z-scores are generally expressed to 2 decimal places. That's how they are in the table. That's how we'll express them here. And the areas, or the probabilities, because they're the same thing, are always expressed to 4 decimal places. So I don't have to say anything about rounding here. You're always going to express these answers to 4 decimal places. Now, number 4 says, suppose a team of biologists has been studying the Pinedale Children's Fishing Pond. This is that setup from the 7.4 notes. Let x represent the length of a single trout at random from the pond. Okay, so someone catches 1 trout. The group of biologists has determined that x has a normal distribution with a mean of 10.2 inches and a standard deviation of 1.4 inches. So reading over this means for anyone who catches a single trout in this pond, the average length, the mean length of that trout is 10.2 inches long. And when we plot that entire distribution of all of those trout, the standard deviation is 1.4 inches. So using our answers from problems 1 through 3 in the warm-up, we'll answer what is the probability that a single trout is between 8 and 12 inches long. In other words, what is the probability that x, because remember x represents the length of a single trout, so x is somewhere between 8 and 12 inches long. Well, this is a pretty normal setup for us now. I give you an x value. You don't want to deal with an x value, so you'll convert this entire problem into z-scores, and so you'll express this as z is between two values, and actually, lucky for us, we've already done that. That's what warm-up problems 1 and 2 were saying. So we converted x, that became negative 1.57. We converted 8 for x to negative 1.57. We converted 12 to 1.29, and then we found the area between these in number 3, and we said 8, 4, 3, 3. Okay, so reading this as a probability, like in terms of a percentage, this means that if you walk up to this Pinedale Children's Fishing Pond and you catch one fish, there is an 84.33% chance that that fish is somewhere between 8 and 12 inches long. Okay, so fine. That's great. But remember, in section 7.4, we were kind of moving over to a different distribution. We were not talking about the length of a single fish. We were talking about the average, the mean lengths of a small sample of fish. Because remember, if you remember the setup was that each child at this Pinedale Children's Fishing Pond catches 5 fish. And so we weren't asking about the length of a single one of their fish. We were asking, what's the average length of the 5 that they caught? What happens if you add up all the lengths of the 5 and then divide by 5? So we were talking about x bar, the x bar distribution, rather than the x distribution. And all of this stuff that we just did is only about x. So we're going to modify that in just a few minutes. Okay, so again, we're talking about the sample mean distribution, the x bar distribution, given that our original distribution of just x's is normal. And the fact is this, if x is any normal, that's true. If x is a random variable with a normal distribution, whose mean is mu and whose standard deviation is sigma, let x bar be the sample mean corresponding to random samples of size n. Now, in our children's fishing pond example, n was 5, but it doesn't have to be 5. That's just what we were dealing with last time. So we'll just have small samples of a given size, and that size is going to be called n. The following 3 statements are true. The x bar distribution is also normal. Now that is what we saw last time, and I hinted last time that that was not a coincidence, and this is why. The x bar distribution is also normal. So if x is normal, then x bar distribution is also normal. Now these two things are nice. The mean of the x bar distribution is still the same mean. So I could put a little note on here. The mean does not change. Not change. The mean value does not change. If the mean of the x distribution is mu, then the mean of the x bar distribution is also mu. That said, the standard deviation does change. So the new standard deviation, and we actually call it sigma and then a little subscript x bar. So that tells us it's the standard deviation of the x bar distribution is the original standard deviation divided by the square root of n, and n are those sample sizes. So with that in mind, note the standard deviation of a sampling distribution is called the standard error. We won't use that too much, but you might read that in your future statistical studies. So the question from the warm-up was about the x value, is the length of a single trout. But again, suppose we want to ask a modified question about x bar, the mean length of a certain subset of trout. So the question then would become, what is the probability that the mean length, x bar, of 5 trout taken at random is between 8 and 12 inches? So let me just emphasize the difference between these questions. In the warm-up, we talked about the probability that a single, it's annoying, that a single trout is between 8 and 12 inches. Just one trout, you catch one trout, what's the probability that that one trout is between 8 and 12 inches long, which was a fairly high probability, 84.33%. Now we're asking, what is the probability that the mean length of 5 trout is between 8 and 12 inches? So now you catch 5 and you measure all of their lengths. What is the probability that the average length of those 5 trout is somewhere between 8 and 12 inches? Now, if I'm writing this out symbolically, this is how we would write it. The probability that now x bar, because now we're talking about the mean length, is somewhere between 8 and 12 inches long. This is a little bit different than the probability that we wrote on page 1, because on page 1, of course, we only used x. We were just talking about the length of one trout, whereas now we're talking about the average length, in this case, of 5 trout. There's n. There's that sample size. So the nice thing for you is that the process does not change at all. I'm giving you these x bar values. You don't want to use x bar values. You want to use z-scores. So we're going to convert these two, 8 and 12, values to z-scores. Now, you might be thinking, we already did that because we converted x to z right back here. And remember, in this case, we were given that the mean was 10.2 and the standard deviation is 1.4, and that's what we used to convert these to z-scores. We're basically going to do the same thing. We're using the same two values, 8 and 12, and the mean doesn't change. The one thing that does change is that standard deviation. So our answers are going to be different because now our standard deviation is different. So let's write this down. Our mean, and I'm going to put a little subscript x bar because now we're talking about the sampling distribution, so the x bar distribution. Well, our mean is still 10.2. That does not change. But our standard deviation of this new x bar sampling distribution does change. And the way that we get that is using this formula, sigma over the square root of n. You have to be really careful about your notation here because sigma and sigma sub x bar, these are two different numbers. So make sure that you're very careful about this subscript notation when it is necessary. Now our original standard deviation, sigma, was 1.4. And now we're going to divide that by the square root of the sample size, in this case 5. So 1.4 divided by the square root of 5. I'm going to round this to 2 decimal places. So when I throw that into my calculator, I get 0.63. Okay, so here's the mean that we're going to use, and here's the standard deviation that we're going to use. And honestly, other than this little change, the strategy now is exactly the same as the warm-up. So I'm going to take 8 and I'm going to take 12. I'll convert them to z-scores, and then I'm going to subtract the areas from the table. So let's do the first one. Z equals, now I'm going to be using my x bar minus mu sub x bar over sigma sub x bar. So I'll start with 8 minus the mean. Well, the mean actually doesn't change. It's still 10.2. Over the standard deviation, that does change. It's 0.63. And when I put those values into my calculator, I get negative 3.49. Very small z value. I'm going to do the same thing for the x bar value of 12. So I'll do 12 minus the mean, 10.2, over the standard deviation, 0.63. And I throw those into my calculator, and I get something around 2.86. Okay, so now these are my two z-scores. So converting this problem, this statement here, to the language of z now gives me negative 3.49 and 2.86. So the problem becomes, what is the probability that z is between negative 3.49 and 2.86? Okay, so I'm going to reference that table that you've marked at the end of section 7.3. And let's see, the larger area, so the one for 2.86. Now, if you haven't had a chance to find it, pause the video now and find these two areas from the table. So I'll hope you've had a chance to do that. The larger area is 0.9979. Make sure that you verify that. Make sure you know how to find that one. The smaller area, the one associated with negative 3.49, is 0.0002. And so subtracting those, larger area minus smaller area, I get 0.9977. Okay, that's a really high probability, 99.77% probability that you catch 5 trout, and the average length of those 5 trout is between 8 and 12 inches. So that leads us to more of a conceptual question here. Why are the probabilities for x and the sampling distribution, x bar, different? Why would these be different? Well, I guess just from an algebraic point of view, they have different standard deviations. So they're slightly different distributions. They do have different standard deviations. But also, we found a pretty high probability that a single trout was between 8 and 12 inches long. I mean, 84.33% that a single trout, that you catch one trout and it's between 8 and 12 inches. Well, if there's a pretty high probability that something happens for one trout, then there's definitely a higher probability that a larger sample would sort of tend toward these values. So like, okay, maybe you catch one trout and it's, I don't know, 7 inches long. It's a little bit on the smaller side for this particular sample that we're looking at, 8 and 12 inches. But we kind of know that if you increase the size of your sample, then your statistical values will get closer and closer and closer to like the average value, right? We talked about this earlier in the course, something called the law of large numbers. So if you catch 5 trout, then it seems like there's a much higher probability, and we just verified it, that the average, that over time, the lengths would average out to somewhere between 8 and 12. And that's what we saw, 99.77%. Really, really, really high, like very close to 100. Okay, so there was one sort of caveat that we didn't talk about on the previous page. There was one big assumption that we had to make in this fact. The fact that we had to assume over here was that your x distribution already started as normal. So if I was summarizing this, it's like if x is normal, then x bar is also normal, which is great. Okay, so that's a useful fact. But this is also a pretty big assumption that x is normal. X is not always going to have a normal distribution. We like it when it does. We like it when we can deal with data that's normally distributed, but the fact is in the real world, we don't always deal with data that's normally distributed. So my question would be, what if our original data is not normal? What if we don't start with a normal distribution? Then what happens to this x bar distribution? And that is addressed here in something called the central limit theorem. So if x follows any distribution at all, and what I mean by that is like it could have a whole lot of skew, it could be bimodal, something like that. But it doesn't have to be normal. So x possesses any distribution with a mean mu and a standard deviation sigma, then the sample mean x bar, based on a random sample of size n, will have a distribution that approaches the distribution of a normal random variable. It gets closer and closer and closer to normal as n increases, as your sample size increases. Now this is, kind of close to like what we were talking about with the law of large numbers a while ago. As your sample size increases, your sampling distribution gets friendlier and friendlier and friendlier. And what we mean in this case is that it approaches a normal shape. Now, on that normal distribution, the mean will still be mu, so the mean does not change. And the standard deviation is that same formula that we just went over, sigma divided by the square root of n. So you just edit your standard deviation just a little bit. So in other words, to summarize this whole thing, no matter what distribution x has, the distribution of x bar, the means, gets closer and closer to normal as the sample size gets larger. Now, let me just write out these formulas in a little bit friendly bulleted way. First of all, the mean of our sampling distribution is the original mean, but again, we do write it with this subscript just to denote that these are different means. The standard deviation of the sampling distribution is sigma, the original standard deviation, divided by the square root of n, the sample size. And this is the same formula that we've used before. This is the one to convert x's to z's. So x minus mu over sigma, this is just adapted to these new values. Now there's a key criterion here. To convert the x bar distribution to the standard normal when n, your sample size, is greater than or equal to 30. This is really important. This is the cutoff value. Your sample size has to be larger than or equal to 30. And that's what we're talking about back here on the previous page where it says that the x bar distribution approaches normal as n increases. Well, as n increases, you kind of might be wondering, well, how large does it have to be? How large does it have to be till we can consider this distribution normal? And the answer is 30. 30 is the cutoff. This is what we need. As long as your sample size is larger than or equal to 30, we are all good to assume that x bar has a normal distribution. So let's put this to work. A certain strain of bacteria occurs in all raw milk. Let x be a milliliter of milk. So this is like a certain spread of data that represents 1 milliliter of milk. The health department has found that if the milk is not contaminated, then x has a distribution that is more or less mound-shaped and symmetrical. Okay, when we read this phrase, it's like a casual way of saying normal. A normal distribution is mound-shaped and symmetric. So the mean of the distribution for x is mu equals 2500. the standard deviation is 300. In a large commercial dairy, the health inspector takes 42 random samples of the milk produced each day. At the end of the day, the bacteria count in each of the 42 samples is averaged to obtain the sample mean bacteria count X bar. Assuming the milk is not contaminated, what is the distribution of X bar? So, well, I mean, we just kind of talked about we talked about a couple things here. So there are two different ways to answer this. First of all, because our original distribution X has a normal shape, we can say if X is normal, then X bar is also normal. And that's what's going on here. So what is the distribution of X bar? Well, because X started out as normally distributed, X bar is also normally distributed. Also, if you were concerned about this phrase, if you were concerned like, well, it doesn't really say that it's normal. I mean, it says it's mound-shaped and symmetrical, but maybe that's like not close enough to normal. Don't worry, because this is the cutoff for, like, we don't have to worry about the X distribution as long as our sample size is greater than or equal to 30. And in this case, our sample size is 42, which is definitely bigger than or equal to 30. So we actually didn't care about our original distribution being normal. Our sample size is big enough that we could have had any distribution to start with. They could have said X has a distribution that is terrible and bimodal and has a bunch of skew or something. It doesn't matter. 42 is big enough that our X bar distribution, our sampling distribution, is also normal. Okay, so we'll say a little bit more about this. We know that the X bar distribution is normal. When we describe a distribution, we should talk about not only its shape, but we should talk about the mean, and we should talk about the standard deviation. And I'm going to make sure to include these subscripts here because I don't want to use the same letters that have already been used, mu and sigma. Those go with a different distribution. So I'm going to say mu sub X bar and sigma sub X bar. Now remember, the mean does not change. The new mean is exactly the same as the old mean. So if the old mean was 2,500, the new mean is also 2,500. The standard deviation, however, does change. So we need to adjust our standard deviation by dividing it by the square root of the sample size. So let's do that. Our old standard deviation was 300. I'm going to divide it by the square root of my sample size, which is 42. And when I throw this into my calculator, it comes out 46.3 about. Okay, so this is how we describe a distribution. We'll talk about its shape. You also give the mean and you give the standard deviation. Now, question number 2. Assuming the milk is not contaminated, what is the probability that the average bacteria count X bar for one day is between 2350 and 2650 bacteria per milliliter? In other words, what is the probability that X bar is between 2350 and 2650? So this is what we're looking for. Now, same sort of strategy that we've used this entire time. I give you some random variable. You don't want to deal with any random variable. You want to convert this to standard units. In other words, you want to convert these values to Z. So let's do that over here. Z equals, so I'll start with my first X value, 2350. 2350. I'm going to subtract the mean, 2500. And I will divide by the standard deviation, 46.3. And when I throw that into my calculator, I find a Z-score of negative 3.24. So this is going to be my new probability question, probability that z is between negative 3.24 and something else. So I'll do this now for the larger value. If z equals 2650, I'll subtract 2500, the mean, divide by 46.3, the standard deviation, and throwing that into my calculator, I find 0.0006. No, that's not true. I am jumping ahead. That's absolutely not true. I find 3.24. And I think I just gave away the next part. Okay, so pause the video now, reference that formula, and find these two areas. We're going to subtract the smaller area from the larger area. I'll give you a second to do it. So hopefully you found on the table that the larger area, the one associated with 3.24, is 0.9994, and the smaller area, which I gave away, is 0.0006, which means that the difference between them is 0.9988. In probability language, 99.88%. So what is the probability that the average bacteria count, X bar, for one day is somewhere between 2350 and 2650 bacteria per milliliter? It's almost 100%. It's 99.88%. And it was okay for us to do this and use all these facts that we know about normal distributions because our sample size was big enough. So just to clarify again, like why this is a friendly process, if we don't have a normal distribution, we can't convert to z. Z is the standard normal, and to convert to the standard normal, we need to be on a normal curve to begin with. So it was very important that we figured out, that we concluded that X bar was a normal distribution. Otherwise, we couldn't have used this tactic to find this probability. We couldn't have converted to z. Okay, so at this point, you should pause the video and try these I really understand this questions. I'll go over them in just a moment. Okay, hopefully you've had a chance to try these problems, but let's go through these one at a time. The first one says, suppose X has a normal distribution with mean mu equals 18 and standard deviation 13. If you draw random samples of size 5, there's n, from the X distribution, and X bar represents the sample mean, what can you say about the X bar distribution? And how could you standardize the X bar distribution? Well, what we can say here is if X already has a normal distribution, then for sure X bar has a normal distribution. If X is normal, then X bar is normal. You might have been concerned about this small sample size. It's definitely below that 30 cutoff, but in this case we don't need to worry about it because X already was normal, so X bar for sure is normal. The time that you're concerned about that 30 is when your original distribution is not normal. That's when we really have to worry about our sample sizes being big enough. So X bar definitely has a normal distribution, and so now we will talk a little bit about the mean and the standard deviation of this normal distribution. Because again, when we're describing a distribution, we describe its shape, and then we also talk about the mean and the standard deviation. So the mean, the new mean, the X bar mean, well, this one's the friendly one. It's exactly the same as the old mean. The mean does not change. So mu sub X bar is still 18. The standard deviation, on the other hand, that does change. We have to adjust the old standard deviation by dividing by the square root of the sample size. So 13 divided by the square root of 5, and I'm going to put that into my calculator real quick. 13 divided by the square root of 5. And so when I do that, I find a standard deviation of 5.81. And I think that answer at the bottom is wrong. 5.81. So we take our original standard deviation and we divide by the square root of the sample mean, and I'm pretty sure, unless I just looked at that wrong. Yeah, that's not right. We'll say 5.81 there. That's how that should be. Okay, so to standardize the x distribution, we would just use the formula x bar. When you say standardize, that just means to turn it into a z value. X bar minus the mean, which was 18, divided by the standard deviation, 5.81. Okay, number 2. Suppose you know the x distribution has a mean of 7.5 and a standard deviation of 12, but you have no information as to whether or not the x distribution is normal. If you draw samples of size 30 from the x distribution and x bar represents the sample mean, what can you say about the x bar distribution? And how could you standardize it? Well, this is a really important phrase here. If you have no information as to whether or not the x bar distribution is normal, that's when you start to look at this sample size. That's when we need the greater than or equal to 30 cutoff. And we just barely made it here. Our sample size is 30, which means that our x bar distribution is normal. So x bar is normally distributed. So we'll describe the shape. We will describe, we'll come up with the mean. This one's the easy one. The mean is the same as the old mean. And the standard deviation. So the new standard deviation for x bar is the old standard deviation, but divided by the square root of the sample size. And so let me throw that into my calculator. 12 divided by the square root of 30. And I find 2.19. I'm going to round it to 2.2. There's my standard deviation. So how could you standardize the x bar distribution? Meaning, how can you change it over into z's? I would use the formula z equals, I would take an x bar value, subtract the mean, which is 75, and divide by the standard deviation, 2.2. That's the formula we would use. Number 3, suppose you did not know if x had a normal distribution. Would you be justified in saying that the x bar distribution is approximately normal if the sample size were n equals 8? Well, if you don't know anything about your original distribution, you cannot say that the x bar distribution is normal unless you have that greater than or equal to 30 criterion met, and 8 is certainly not greater than or equal to 30. So no, we can't say that x bar it has a normal distribution because the sample size is not big enough. So we need n has to be greater than or equal to 30. You have to have that happen. Now, if we knew that our original distribution was normal, then in that case, we wouldn't care about this 30 cutoff. But if we don't know, then we need our sample size to be big enough. Last one, number 4. Let x represent the time it takes for a car to pass through a tunnel. Suppose the x distribution has a mean of 12.1 minutes and a standard deviation of 3.8 minutes, and that the x distribution is mound-shaped and symmetrical. Okay, again, this pretty much means normal. Let x bar represent the sample mean based on samples of size 50. That's definitely greater than or equal to 30, so it turns out this phrase didn't even matter at all. Describe the X-bar distribution. Well, a couple things here. It sounds like X already started with a normal distribution, so X-bar will then have a normal distribution. But because it doesn't actually use the words normal, it doesn't even matter because our sample size is bigger than 30. So X-bar is normally distributed. X-bar has a normal distribution. And then with that, we will find the mean, which again doesn't change. This is the same as the old mean, 12.1, and the new standard deviation, which is equal to the old one, but divided by the square root of that sample size, which is 50. So throwing that in my calculator, 3.8 divided by the square root of 50, I get 0.5374. I'm going to say 0.54. So there is my new standard deviation. Last one, find the probability that the sample mean is between 11 and 13. Okay, so again, I'm giving you some X values, X-bar values. You don't want to deal with these X values. You always want to deal with the standard normal. So I want to convert these over to Z scores. I want to rewrite this problem in terms of Z. And so one by one, I'm going to convert these over. So 11, I'll start with 11. Z equals 11 minus the mean, which is 12.1, over the standard deviation, 0.54. And so divided by 0.54, I get negative 2.04. And I'm rounding that to 2 decimal places because that's how we always express our Z values. On the table, you'll see that you always have Z values rounded to 2, so I'm taking that negative 2.037037 that I just found on my calculator and expressing it as 2.04. And then I will do the same thing for Z, for X equals 13, X bar equals 13. So 13 minus 12.1 over 0.54. And I find 1 point, looks like 6 is repeating, but I'm going to round it to 6.7. Okay, so now I'm going to reference the table. I have to grab mine. Let's see. So looking at my table, the area associated with Z equals 1.67, I'm finding 0.9525. That's the larger area. And then on the other side of the table, negative 2.04 is 0.0207. And I will subtract those to get my final answer, minus 0.0207, and I found 0.9318. So the probability that we take 50 cars and we time them passing through this tunnel, the probability that the average time for those 50 cars, so again, not an individual car, but the average time for this sample of 50 cars, the probability that that average time is somewhere between 11 and 13 minutes is 93.18%. So, we're going to sort of deviate from this the next time we talk. The next time we talk, we're going to essentially do the same process, but we're going to apply it to a binomial. distribution. So maybe before you watch the 7.6 video, just review, let's see, what section was it? Review section 6.3? 6.2. Review sections 6.2 and 6.3. Just like read through your notes real quick, 6.2 and 6.3, because they are about binomial distributions, and we're going to be applying all this stuff to binomial distributions in the last section of chapter 7. I'll see you then.